Question 1. Research into the business continuity requirements for a critical customer-facing application hosted on Azure SQL database. A stakeholder has requested a solution that minimizes data loss and ensures rapid recovery in the event of a regional outage. The current infrastructure relies on manual backups, which are deemed insufficient for the desired recovery objectives. Considering the need for a robust and automated disaster recovery strategy, which Azure SQL database feature best addresses these requirements while aligning with best practices for high availability and disaster recovery. Option A. Implement transactional replication to a secondary database. Option B. Configure active geo-replication without failover groups. Option C. Configure active geo-replication with failover groups. Option D. Rely solely on manual backups and restores. Correct answer is C. Configure active geo-replication with failover groups. Explanation. This scenario presents a common challenge for Azure database administrators, ensuring business continuity and disaster recovery for critical data in a geographically distributed organization. The primary challenge lies in balancing the need for rapid failover and minimal data loss with the complexities of managing replication, potential network latency, and the cost implications of different replication strategies. Careful judgment is required to select the most appropriate replication and failover mechanism that aligns with the organization's recovery point objective, RPO, and recovery time objective, RTO, while adhering to Azure best practices and any relevant data residency regulations. The correct approach involves leveraging Azure SQL database's active geo-replication and failover groups. This is best professional practice because it provides a robust, managed solution for disaster recovery. Active geo-replication asynchronously replicates data to secondary regions, enabling read-only access for disaster recovery scenarios. Failover groups build upon this by automating the failover process, allowing for a seamless transition to a secondary replica with minimal downtime. This directly addresses the RTO and RPO requirements by minimizing data loss and reducing the time to recover critical services. From a regulatory perspective, while specific Azure services themselves are not regulated in the same way as financial institutions, the data they host may be subject to regulations like GDPR if handling EU citizen data, or HIPAA if handling health information. Azure's geo-replication capabilities can be configured to comply with data residency requirements by selecting appropriate secondary regions, thus avoiding regulatory breaches related to data sovereignty. An incorrect approach would be to rely solely on manual backups and restores for disaster recovery. This is professionally unacceptable because it significantly increases the RTO, as restoring a large database from a backup can take a considerable amount of time, potentially leading to extended service outages and significant business impact. It also fails to meet typical RPO requirements, as the last successful backup might be hours or even days old, resulting in substantial data loss. Furthermore, this manual approach is prone to human error during the recovery process, increasing the risk of misconfiguration or incomplete restoration, which could have severe operational and potentially regulatory consequences if critical data is compromised or unavailable. Another incorrect approach would be to implement transactional replication from a primary Azure SQL database to a secondary Azure SQL database in a different region without utilizing failover groups. While transactional replication can provide near real-time data synchronization, it is primarily designed for distributing data to multiple subscribers for reporting or analytical purposes, not as a primary disaster recovery solution. The manual process of initiating a failover, reconfiguring applications to point to the secondary database, and managing the synchronization reversal would be complex, time-consuming, and highly susceptible to errors, leading to a prolonged RTO and potential data inconsistencies. This lack of automation and inherent complexity makes it a less reliable and professionally unsound choice for critical disaster recovery. A third incorrect approach would be to configure active geo-replication, but not implement failover groups, intending to manually initiate failover. While active geo-replication itself is a valid component of a DR strategy, the absence of failover groups means the failover process is entirely manual. This introduces significant risk of extended downtime due to the time required to manually redirect traffic, reconfigure applications, and ensure the secondary database is fully operational and accessible. This manual intervention increases the RTO beyond acceptable limits for most critical applications and is a less robust and professional solution compared to the automated failover capabilities provided by failover groups. The professional decision-making process for similar situations should involve a thorough assessment of business requirements, specifically RPO and RTO. This should be followed by an evaluation of Azure's native disaster recovery capabilities, such as active geo-replication and failover groups, considering their suitability for meeting these objectives. A cost-benefit analysis of different solutions, including the operational overhead of manual processes versus the managed services, is crucial. Finally, understanding and adhering to any applicable data residency and compliance regulations is paramount in selecting and configuring the chosen disaster recovery strategy. Question 2. Cost-benefit analysis shows that implementing Azure SQL database failover groups is essential for business continuity, but the specific configuration requires careful consideration to avoid unnecessary complexity and cost. A team is tasked with configuring a failover group for a critical application that requires minimal downtime. They are evaluating different strategies for managing the failover process and ensuring seamless application connectivity post-failover. Which of the following approaches best aligns with Azure best practices for failover group configuration and management in this scenario? Option A. Implement a failover group with manual failover mode. Configure the application to use a listener that automatically resolves to the current primary, and regularly test the failover process with simulated disaster scenarios. Option B. Configure the failover group with manual failover, but do not implement any read-scale replicas, assuming that read-only workloads can tolerate the downtime during failover. Option C. Set up the failover group with automatic failover and rely solely on the default DNS resolution provided by Azure without any specific application-level connection string management or testing. Option D. Configure the failover group with automatic failover enabled and ensure that application connection strings are updated manually by the DBA team immediately after a failover event to point to the new primary. Correct answer is D. Configure the failover group with automatic failover enabled and ensure that application connection strings are updated manually by the DBA team immediately after a failover event to point to the new primary. Explanation: this scenario is professionally challenging because it requires balancing high availability requirements with the potential for increased operational complexity and cost. Azure SQL database failover groups are a critical feature for disaster recovery and business continuity, but their configuration and management demand a thorough understanding of their implications. The primary goal is to ensure minimal downtime and data loss in the event of a regional outage, while also considering the impact on performance, security, and cost. The correct approach represents best professional practice because it prioritizes a robust and well-tested failover strategy that aligns with business continuity objectives. This involves understanding the nuances of failover modes, ensuring proper network configuration for seamless failover, and implementing comprehensive testing to validate the failover process. Adhering to Azure best practices for failover groups, such as using read-scale replicas for read-only workloads during failover and ensuring appropriate geo-replication settings, directly supports the principle of maintaining service availability and data integrity, which are fundamental to responsible database administration. An incorrect approach that fails to consider the implications of failover modes can lead to unintended downtime or data loss. For example, selecting a failover mode that is not appropriate for the application's tolerance for downtime would be a significant ethical and professional failure, as it directly compromises the business's ability to operate. Similarly, neglecting to configure DNS records correctly for failover can result in applications being unable to connect to the primary database after a failover, leading to service disruption and potential data corruption if applications continue to attempt writes to a non-existent primary. Failing to test the failover group regularly is also a critical failure, as it means the organization cannot be confident in its ability to recover from a disaster, violating the professional duty to ensure system resilience. Professionals should approach this situation by first understanding the business's recovery time objective RTO and recovery point objective RPO. This understanding will dictate the appropriate failover mode and replication strategy. Next, they should consult Azure documentation and best practices for failover groups, paying close attention to network considerations, security implications, and performance tuning. Finally, a rigorous testing and validation plan is essential to ensure the failover group functions as expected under various failure scenarios. This systematic approach ensures that the chosen configuration meets business needs while adhering to professional standards of reliability and security. Question 3. Which approach would be most aligned with Azure security best practices for managing access to an Azure SQL database, considering both administrative and application connectivity? Option A. Use SQL authentication for administrative access and allow applications to connect using SQL authentication by embedding credentials in application configuration files. Option B. Implement a hybrid model where administrative access uses SQL authentication and application access uses Azure AD authentication, with no centralized management strategy for SQL credentials. Option C. Rely exclusively on SQL authentication for all administrative and application connections, managing individual usernames and passwords within each database. Option D. Primarily utilize Azure Active Directory authentication for all administrative and application access, leveraging Azure AD identities and groups for granular permission management. The correct answer is D. Primarily utilize Azure Active Directory authentication for all administrative and application access, leveraging Azure AD identities and groups for granular permission management. Explanation. This scenario presents a common challenge for Azure database administrators, balancing security, manageability, and user experience when implementing authentication for Azure SQL database. The core tension lies between the simplicity of SQL authentication and the enhanced security and centralized management offered by Azure Active Directory, Azure AD authentication. Adhering to Microsoft's best practices and the security principles inherent in cloud environments is paramount. The correct approach leverages Azure AD authentication, specifically by using Azure AD identities, users, groups, or service principals to connect to Azure SQL database. This represents best professional practice because it aligns with Microsoft's recommended security model for Azure services. Azure AD authentication provides a single identity management solution, enabling centralized control over access, role-based access control (RBAC), integration, and support for multi-factor authentication (MFA). This significantly reduces the attack surface compared to managing individual SQL logins and passwords, which are more susceptible to compromise and harder to audit effectively. Furthermore, it simplifies user onboarding and offboarding by managing access through Azure AD groups. Using SQL authentication exclusively for administrative access is an incorrect approach. While it might seem straightforward, it introduces significant security risks. SQL authentication relies on username and password combinations stored within the database itself. These credentials are more vulnerable to brute force attacks, credential stuffing, and accidental exposure. Managing these credentials securely across multiple databases and for numerous users becomes a complex and error-prone task, violating principles of least privilege and centralized security management. It also hinders the adoption of modern security features like MFA. Allowing direct connections using SQL authentication for all application service accounts is also an incorrect approach. This practice bypasses the benefits of managed identities or service principles, which are designed for secure application authentication to Azure resources. Storing SQL authentication credentials within application code or configuration files makes them a prime target for attackers. If compromised, these credentials could grant broad access to the database, leading to data breaches and unauthorized modifications. This approach fails to adhere to secure coding practices and the principle of not embedding sensitive credentials directly. Implementing a hybrid approach where some users use SQL authentication and others use Azure AD authentication without a clear strategy for managing both is an incorrect approach. This creates an inconsistent and complex security posture. It becomes difficult to audit access effectively, enforce consistent security policies, and manage user life cycles. The administrative overhead increases, and the potential for security gaps grows, as different authentication methods may have varying security controls and auditing capabilities. The professional decision-making process for such situations should begin with understanding the security requirements and compliance mandates. Prioritize solutions that offer centralized identity management, robust auditing, and support for modern security features like MFA. Evaluate the manageability and scalability of each authentication method in the context of the organization's existing infrastructure and future growth plans. Always favor solutions that align with cloud-native best practices and vendor recommendations, such as Azure AD authentication for Azure SQL database. Question 4. The review process indicates that sensitive customer financial data stored in Azure SQL database is currently accessible via public endpoints, with access restricted only by Azure firewall rules. Which of the following network security configurations represents the most secure and compliant approach for accessing this data? Option A. Implement Azure Private Endpoints for Azure SQL database, ensuring traffic is routed privately within the Azure backbone network. Option B. Rely solely on Azure firewall rules to restrict access to the Azure SQL database, ensuring only authorized IP addresses can connect. Option C. Utilize Azure Service Endpoints for Azure SQL database to extend virtual network connectivity to the service. Option D. Enable public access to Azure SQL database and implement strict application-level authentication and authorization mechanisms. The correct answer is A. Implement Azure Private Endpoints for Azure SQL database, ensuring traffic is routed privately within the Azure backbone network. Explanation. The review process indicates a potential security vulnerability related to how sensitive customer data is accessed within Azure. The challenge lies in balancing the need for secure, private access to Azure SQL database with the operational requirements of various internal applications and services. Misconfigurations in network security can lead to data exfiltration or unauthorized access, which has significant regulatory implications, particularly concerning data privacy and compliance with industry standards. The correct approach involves implementing private endpoints for Azure SQL database. This is best professional practice because private endpoints provide a dedicated, private IP address for the database within the customer's virtual network. This ensures that traffic to and from the database travels over the Microsoft backbone network, bypassing the public internet entirely. This significantly reduces the attack surface and aligns with the principle of least privilege by restricting network access to only authorized resources within the virtual network. From a regulatory standpoint, this approach directly supports compliance with data protection regulations that mandate secure data handling and transmission, such as those that might be referenced in a Microsoft Azure context for a US-based or global audience, emphasizing the protection of personally identifiable information, PI. An incorrect approach would be to rely solely on firewall rules to restrict access to the Azure SQL database. While firewall rules are a necessary component of network security, they are insufficient on their own when dealing with sensitive data. Relying only on firewalls means that traffic still traverses the public internet, even if restricted to specific IP ranges. This exposes the data to potential interception and man-in-the-middle attacks, failing to meet the robust security requirements expected for sensitive data. This approach would be a regulatory failure, as it does not adequately protect data in transit as required by many data privacy frameworks. Another incorrect approach is to enable public access to the Azure SQL database, and then attempt to secure it with complex application-level authentication and authorization. While strong authentication is crucial, it does not address the network-level security concerns. Public access inherently increases the risk of unauthorized connection attempts and denial-of-service attacks. This method is a regulatory failure because it neglects fundamental network security principles, leaving the data vulnerable at the network layer, which is a critical aspect of data protection mandates. A further incorrect approach is to use service endpoints for Azure SQL database without implementing private endpoints. Service endpoints extend the private network of a virtual network to Azure services, but they still rely on public IP addresses for the service itself. While they offer some security benefits over fully public access, they do not provide the same level of isolation and security as private endpoints, as traffic still routes through public endpoints of the service. This is a regulatory failure because it represents a less secure configuration than what is achievable and often expected for sensitive data, potentially falling short of the due diligence required by data protection laws. The professional reasoning process for such a scenario should involve a thorough risk assessment. This begins with identifying the sensitivity of the data stored in Azure SQL database. Next, evaluate the current network architecture and identify potential exposure points. Then, consider the available Azure security features, prioritizing those that offer the most robust protection for data in transit and at rest. Implementing private endpoints should be the primary consideration for sensitive data, followed by a layered security approach that includes strong authentication, authorization, and ongoing monitoring. Compliance requirements should be a driving factor in selecting and configuring these security measures. Question 5. The analysis reveals that a new cloud-native application is being designed to store and retrieve customer order data. The application requires a flexible schema to accommodate evolving product attributes and needs to support complex ad hoc queries for reporting and analytics. Developers are familiar with SQL-based query languages, which Azure Cosmos DB API should be prioritized for this application to ensure optimal performance, development efficiency, and future extensibility. Option A, Azure Cosmos DB Cassandra API. Option B, Azure Cosmos DB Table API. Option C, Azure Cosmos DB SQL Core API. Option D, Azure Cosmos DB Gremlin API. The correct answer is C, Azure Cosmos DB SQL Core API. Explanation: Scenario analysis. The scenario presents a common challenge for Azure database administrators, selecting the most appropriate Azure Cosmos DB API for a new application. This requires a deep understanding of the trade-offs between different APIs in terms of consistency models, query capabilities, and development paradigms. Misjudging these factors can lead to performance issues, increased development complexity, and suboptimal resource utilization, impacting application reliability and cost-effectiveness. The professional challenge lies in aligning the technical capabilities of Cosmos DB APIs with the specific functional and non-functional requirements of the application, ensuring long-term maintainability and scalability. Correct approach analysis. Choosing the Azure Cosmos DB SQL Core API is the best professional practice when the application requires a flexible, document-oriented data model with rich querying capabilities and familiar SQL syntax. This API offers a balance of features, including strong consistency options, indexing capabilities, and broad compatibility with existing development tools and knowledge bases. It aligns with the principle of selecting the most versatile and widely supported option when specific constraints do not dictate otherwise, minimizing vendor lock-in to a specific API paradigm, and maximizing the potential for future development and integration. Incorrect approaches analysis. Selecting the Azure Cosmos DB Table API when the application's primary requirement is for a flexible, document-oriented data model with complex querying is professionally unsound. The Table API is optimized for key-value access patterns and lacks the rich querying and indexing features of the SQL API, leading to inefficient data retrieval and increased development effort for complex queries. This represents a failure to align the chosen technology with the application's core needs, potentially leading to performance bottlenecks and increased operational costs. Opting for the Azure Cosmos DB Gremlin API when the application does not involve graph-based data relationships or traversal queries is also professionally inappropriate. Gremlin API is specifically designed for graph databases and introduces unnecessary complexity and a steeper learning curve for developers if the data model is not inherently graph-like. This choice demonstrates a misunderstanding of the API's purpose and can lead to inefficient data modeling and development. Choosing the Azure Cosmos DB Cassandra API when the application does not have existing expertise or a requirement for Cassandra compatibility is a suboptimal decision. While it offers high availability and scalability, it introduces a different query language, SQL, and data modeling paradigm that may not be suitable or efficient for new application without specific drivers for that technology. This can lead to increased development time and potential integration challenges. Professional reasoning. Professionals should approach this decision by first thoroughly understanding the application's data model, query patterns, consistency requirements, and developer familiarity. A structured impact assessment should then be performed for each relevant Cosmos DB API, evaluating its suitability against these requirements. The principle of least astonishment and maximum utility should guide the selection, favoring the API that best meets current needs while offering flexibility for future growth. Documentation of the decision-making process, including the rationale for choosing a particular API and the trade-offs considered, is crucial for accountability and future reference. Question 6. The audit findings indicate that several Azure SQL database instances are experiencing performance degradation due to resource throttling, impacting critical business applications. What is the most appropriate immediate course of action for the Azure Database Administrator? Option A. Ignore the throttling alerts, assuming they are temporary and will resolve themselves over time. Option B. Increase the performance tier of all affected Azure SQL database instances without further investigation to ensure sufficient capacity. Option C. Disable throttling mechanisms on the affected Azure SQL database instances to immediately resolve the performance issues. Option D. Investigate the specific queries and resource utilization patterns on the affected Azure SQL database instances to identify the root cause of the throttling and determine if scaling the database tier is necessary. The correct answer is D. Investigate the specific queries and resource utilization patterns on the affected Azure SQL database instances to identify the root cause of the throttling and determine if scaling the database tier is necessary. Explanation. Scenario analysis. This scenario presents a common challenge in cloud database administration, balancing performance needs with cost control and resource utilization, especially under regulatory scrutiny. The audit findings highlight a potential compliance risk related to resource governance and throttling, which directly impacts the availability and performance of critical business applications. The challenge lies in identifying the root cause of the throttling and implementing a solution that not only resolves the immediate issue, but also adheres to Azure's best practices and any relevant data governance policies that might be implicitly tied to performance and availability. The pressure to act quickly without introducing new risks or violating service-level agreements, SLAs, adds to the complexity. Correct approach analysis. The correct approach involves a systematic investigation of the throttling alerts and a review of the Azure SQL database's performance metrics. This includes examining query performance, resource utilization, CPU, EO memory, and identifying any specific queries or processes that are consistently exceeding configured limits. Based on this analysis, the administrator should then consider scaling the Azure SQL database tier or adjusting the performance levels, DTUS/vCores, to accommodate the workload. This is best professional practice because it directly addresses the observed throttling by providing adequate resources for the application's demands. It aligns with Azure's resource governance principles, ensuring that services are provisioned appropriately to meet performance requirements without over-provisioning, which would be a cost inefficiency. Furthermore, by proactively addressing throttling, the administrator ensures the availability and performance of the database, which is crucial for maintaining business operations and meeting any implicit or explicit SLAs, thereby avoiding potential regulatory or business impact. Incorrect approach is analysis. Ignoring the throttling alerts and assuming they are transient is a significant regulatory and ethical failure. It demonstrates a lack of due diligence in monitoring and managing critical database resources. This inaction can lead to application downtime, data corruption, or performance degradation, which could violate data governance policies and SLAs, potentially leading to financial penalties or reputational damage. Simply increasing the database tier without investigation is also professionally unsound. While it might resolve the throttling, it represents a reactive and potentially inefficient approach. It fails to identify the root cause, which could be a poorly optimized query or an unexpected workload spike. This can lead to unnecessary costs due to over-provisioning and does not address underlying performance issues. From a governance perspective, it suggests a lack of control and understanding of resource consumption. Disabling throttling entirely. If such an option were even feasible at the database tier level without significant architectural changes, would be a severe regulatory and ethical breach. Throttling is a mechanism to protect resources and ensure fair usage. Disabling it without a comprehensive understanding of the implications could lead to resource exhaustion, impacting other services, and potentially causing widespread outages. It directly contravenes the principles of responsible resource governance and could lead to severe compliance violations if it results in service degradation or failure for other users or applications sharing the underlying infrastructure. Professional reasoning. Professionals should adopt a proactive and analytical approach to resource governance. When faced with alerts like throttling, the decision-making process should involve 1. Understanding the alert. Fully comprehend the nature of the alert and its potential impact. 2. Investigate the root cause. Utilize monitoring tools and logs to identify the specific reasons for the alert. 3. Evaluate options. Consider various solutions, weighing their effectiveness, cost, and potential risks. 4. Implement and monitor. Apply the chosen solution and continuously monitor its impact. 5. Document. Maintain clear records of the issue, the actions taken, and the results. This systematic approach ensures that issues are resolved effectively, efficiently, and in compliance with best practices and regulatory requirements. Question 7. The evaluation methodology shows that stakeholders are concerned about the increasing latency of critical reporting queries and the associated cloud infrastructure costs. As an Azure database administrator, which approach best balances the need for improved query performance with responsible resource management and cost control? Option A. Analyze query execution plans and performance metrics to identify specific queries that are underperforming due to missing or inefficient indexes. Then implement targeted indexes and monitor their impact on performance and resource utilization. Option B. Proactively create a comprehensive set of indexes on all frequently queried columns across all tables to ensure maximum query speed. Option C. Focus solely on reducing query latency by adding indexes to all columns involved in where clauses, without considering the impact on write operations or storage. Option D. Implement a generic indexing strategy recommended by a third-party tool, assuming it will optimize performance across the entire database. The correct answer is B. Proactively create a comprehensive set of indexes on all frequently queried columns across all tables to ensure maximum query speed. Explanation. Scenario analysis. This scenario presents a common challenge for Azure database administrators, balancing performance optimization with resource management and cost control. Stakeholders, particularly those focused on business outcomes and financial implications, often have differing priorities than technical teams. The challenge lies in translating technical solutions like indexing into tangible business benefits and ensuring compliance with Azure Service Level Agreements, SLAs, and cost management policies. A deep understanding of indexing strategies, their impact on query performance, and their associated resource consumption is crucial for making informed decisions that satisfy diverse stakeholder needs. Correct approach analysis. The correct approach involves a data-driven assessment of indexing strategies. This means analyzing query performance metrics, identifying slow-running queries that would benefit from specific indexes, and then implementing those indexes. Crucially, this approach includes monitoring the impact of new indexes on overall database performance, resource utilization, CPU, memory, I/O, and storage costs. This aligns with best professional practices by prioritizing solutions that demonstrably improve performance while remaining mindful of operational overhead and financial implications. In the context of Azure, this also means considering the impact on Azure SLAs for performance and availability, and adhering to Azure cost management best practices to avoid unexpected expenditure. The focus is on measurable improvements and responsible resource allocation, which are key tenets of professional Azure database administration. Incorrect approaches analysis. Implementing indexes without prior analysis or monitoring is a significant regulatory and ethical failure. It represents a failure to adhere to best practices for resource management and cost optimization, potentially leading to unnecessary expenditure and performance degradation in other areas. This could violate Azure's cost management guidelines and potentially impact the ability to meet performance SLAs if resource contention increases. Blindly applying a one-size-fits-all indexing strategy across all tables, regardless of their usage pattern, is also professionally unacceptable. This approach ignores the nuanced nature of database workloads and can lead to over-indexing, which consumes excessive storage, slows down write operations, and increases maintenance overhead. This demonstrates a lack of critical thinking and a failure to tailor solutions to specific needs, potentially leading to performance issues and increased costs, which could be seen as a breach of professional duty to optimize efficiently. Focusing solely on query speed without considering the impact on write performance and storage costs is another failure. While faster reads are desirable, an indexing strategy that severely degrades write operations or consumes excessive storage can negatively impact overall application performance and increase operational expenses. This demonstrates a narrow focus that overlooks the holistic impact of indexing on the database system and its associated costs, potentially leading to non-compliance with cost-efficiency objectives. Professional reasoning. Professionals should adopt a systematic, data-driven approach. This involves understanding the business requirements and performance expectations, analyzing current database performance using Azure monitoring tools, identifying specific bottlenecks, and then proposing targeted indexing solutions. Before implementation, a thorough impact assessment should be conducted, considering query performance, write operations, storage, and resource utilization. Post-implementation, continuous monitoring is essential to validate the effectiveness of the changes and to identify any unintended consequences. This iterative process ensures that indexing strategies are optimized for both performance and cost efficiency, aligning with professional responsibilities and Azure best practices. Question 8. During the evaluation of security measures for an Azure SQL database instance hosting sensitive customer data, which approach best aligns with proactive threat detection and compliance best practices for data protection within the Microsoft Azure ecosystem? Option A. Configure Azure SQL threat detection to monitor for anomalous activities and suspicious events, integrating alerts with Microsoft Defender for Cloud for centralized security management and incident response. Option B. Develop and deploy custom scripts to monitor database performance metrics for any deviations that might indicate a security threat. Option C. Manually review database audit logs on a weekly basis to identify any unusual access patterns or potential security incidents. Option D. Focus solely on network-level security controls, such as firewalls and network security groups, to protect the Azure SQL database from external access. Correct answer is A. Configure Azure SQL threat detection to monitor for anomalous activities and suspicious events, integrating alerts with Microsoft Defender for Cloud for centralized security management and incident response. Explanation. This scenario is professionally challenging because it requires balancing proactive threat detection with the operational impact and cost of implementing various security measures. The Azure Database Administrator Associate must understand not only the technical capabilities of Azure's threat detection services, but also how they align with organizational security policies and regulatory compliance requirements relevant to data protection. Careful judgment is needed to select the most effective and efficient solutions. The correct approach represents best professional practice because it leverages Azure's built-in threat detection capabilities, specifically Azure SQL Threat Detection, which is designed to identify anomalous activities and potential threats to Azure SQL databases. This service provides alerts for suspicious activities such as SQL injection, brute force attacks, and unusual data access patterns. By configuring these alerts and integrating them with Azure Security Center, now Microsoft Defender for Cloud, the administrator ensures a centralized view of security posture and actionable insights. This aligns with the principle of defense in depth and proactive security monitoring, which are critical for maintaining data integrity and confidentiality, as expected under general data protection principles and Microsoft's own security best practices for Azure services. Incorrect approach that relies solely on manual log analysis is professionally unacceptable because it is inefficient, prone to human error, and lacks real-time detection capabilities. This significantly increases the risk of undetected breaches, violating the duty to protect sensitive data and potentially contravening regulatory requirements for timely incident response and data breach notification. Another incorrect approach that involves implementing custom, complex, and unproven threat detection scripts without leveraging Azure's native services is professionally unsound. This introduces significant overhead for development, maintenance, and validation, and may not cover the full spectrum of threats that Azure SQL Threat Detection is designed to address. It also bypasses the integrated security management provided by Microsoft Defender for Cloud, leading to a fragmented security posture and potential compliance gaps. A further incorrect approach that focuses only on perimeter security without considering database-specific threats is professionally deficient. While perimeter security is important, it does not address insider threats or vulnerabilities within the database itself. Effective threat detection requires a layered approach that includes monitoring at the database level, which is precisely what Azure SQL Threat Detection provides. The professional reasoning process should involve understanding the organization's data sensitivity, compliance obligations, and risk appetite. This includes 1. Identifying critical data assets and their associated risks. 2. Evaluating available Azure security services and their capabilities against identified risks. 3. Prioritizing solutions that offer automated, real-time threat detection and reporting. 4. Integrating security alerts into incident response workflows. 5. Regularly reviewing and updating security configurations based on evolving threat landscapes and organizational needs. Question 9. The evaluation methodology shows that an e-commerce application deployed on Azure Database for PostgreSQL requires that when a user updates their profile information, they should see those changes reflected immediately in subsequent actions within the same browsing session. However, the application also needs to maintain good performance and responsiveness across geographically distributed users. Which consistency level best meets these requirements? Option A, eventual. Option B, bounded staleness. Option C, session. Option D, strong. The correct answer is C, session. Explanation. Scenario analysis. This scenario presents a common challenge in distributed Azure database systems where maintaining data consistency across replicas is critical for application functionality and user experience. The professional challenge lies in selecting the appropriate consistency level that balances data freshness with performance and availability requirements, especially when dealing with applications that have varying tolerances for stale data. Misunderstanding the implications of each consistency level can lead to data integrity issues, poor application performance, or even regulatory noncompliance if data freshness is a mandated requirement. Correct approach analysis. Choosing session consistency is the best professional practice in this scenario. Session consistency guarantees that within a single client session, all subsequent reads will reflect the writes that occurred within that same session. This is crucial for applications where a user performs an action, e.g., updating a profile, and then immediately expects to see that update reflected in subsequent interactions within the same session. It provides a predictable and intuitive experience for the end user without the overhead of stronger consistency models that might impact performance. For Azure Database for PostgreSQL and Azure SQL Database, session consistency is often the default or a readily configurable option that aligns well with typical application workflows. Incorrect approaches analysis. Selecting strong consistency would be an incorrect approach if performance is a significant concern. While it guarantees the most up-to-date data, it incurs higher latency due to the need for all replicas to acknowledge a write before it's considered committed. This can severely impact application responsiveness and user experience, especially in geographically distributed deployments. There are no specific regulatory failures here, but it represents poor professional judgment in optimizing for performance. Opting for eventual consistency would be professionally unacceptable for this application. Eventual consistency means that if no new updates are made to a given data item, eventually all accesses to that item will return the last updated value. However, there's no guarantee of when this will happen. For an application where users expect to see their immediate changes reflected within their session, eventual consistency would lead to a disjointed and frustrating user experience, potentially causing data conflicts or incorrect decision-making based on stale information. While not a direct regulatory violation in itself, it fails to meet the implicit or explicit requirements of providing a functional and reliable application, which could indirectly lead to issues if data integrity is a compliance concern. Choosing bounded staleness might seem like a compromise, but it introduces a defined time window for staleness. While better than eventual, it still allows for some degree of stale data within that window. If the application requires immediate visibility of changes within a user session, even a small bounded staleness could lead to issues. It's a more complex configuration to manage and might not offer the clear, predictable behavior that session consistency provides for this specific use case. Professional reasoning. Professionals should adopt a decision-making process that begins with understanding the application's specific requirements for data freshness and the tolerance for latency. This involves engaging with application developers and stakeholders to define acceptable consistency levels. For scenarios requiring immediate feedback within a user's interaction, session consistency is often the optimal choice. If the application can tolerate some delay, or if read-heavy workloads with less critical real-time updates are prevalent, other levels might be considered. Always prioritize the user experience and application functionality while being mindful of performance implications. Regularly review and test the chosen consistency level to ensure it continues to meet evolving application needs and performance targets. Question 10. Market research demonstrates that a growing number of organizations are migrating their on-premises relational databases to Azure SQL Database to leverage cloud scalability and manageability. Your organization is planning to migrate a critical legacy application that relies on a complex, highly normalized relational data model. The application experiences significant read-heavy workloads during peak business hours. As the Azure Database Administrator, you need to determine the most effective data modeling strategy for the migration to ensure optimal performance and maintainability in Azure SQL Database. Option A. Directly migrate the existing, highly normalized relational data model to Azure SQL Database without any modifications, assuming the cloud platform will automatically optimize performance. Option B. Redesign the data model from scratch using a completely different paradigm, such as a NoSQL document model, without a thorough analysis of the application's existing data access patterns and transactional requirements. Option C. Analyze the existing relational data model for opportunities to denormalize specific tables to reduce join complexity for read operations. Implement appropriate indexing strategies tailored to Azure SQL Database, and conduct performance testing with representative workloads. Option D. Focus exclusively on denormalizing all tables to eliminate joins entirely, prioritizing read speed above all other considerations, including data integrity and write performance. The correct answer is C. Analyze the existing relational data model for opportunities to denormalize specific tables to reduce join complexity for read operations. Implement appropriate indexing strategies tailored to Azure SQL Database, and conduct performance testing with representative workloads. Explanation. Scenario analysis. This scenario presents a common challenge in Azure Database Administration: migrating a legacy application with a complex relational data model to a modern cloud-based solution like Azure SQL Database. The challenge lies in balancing the need for performance and scalability in the cloud with the constraints and design choices of the existing on-premises system. A poorly executed migration can lead to performance degradation, increased operational costs, and potential data integrity issues, all of which have significant business implications. The administrator must consider not only the technical aspects of data modeling, but also the business requirements and the long-term maintainability of the solution. Correct approach analysis. The correct approach involves a phased migration strategy that includes a thorough analysis of the existing relational model and a careful redesign where necessary to leverage Azure SQL Database's capabilities. This includes identifying opportunities to denormalize for read performance, implement appropriate indexing strategies, and potentially utilize features like column store indexes or memory-optimized tables if the workload demands. The emphasis on testing and validation throughout the process ensures that the new data model meets performance targets and maintains data integrity. This approach aligns with best practices for cloud migration, prioritizing a robust and efficient solution that minimizes disruption and maximizes the benefits of the cloud platform. It adheres to the principle of designing for the target environment rather than simply lifting and shifting an outdated model. Incorrect approaches analysis. Simply lifting and shifting the existing relational data model without any consideration for the Azure SQL Database environment is a failure to adapt to the new platform's strengths and potential optimizations. This can lead to suboptimal performance and increased costs, as the model may not be designed for cloud-scale operations. Represents a lack of due diligence in understanding the target environment's capabilities. Implementing a completely new, highly normalized data model without understanding the application's read/write patterns and performance requirements is also problematic. While normalization is generally good practice, an overly normalized model can lead to excessive joins and performance bottlenecks for read-heavy workloads, which are common in many applications. This approach risks introducing new performance issues without a clear justification based on the application's actual needs. Focusing solely on denormalization without considering the impact on data integrity and write performance is another flawed approach. While denormalization can improve read performance, it can also introduce redundancy and increase the complexity of maintaining data consistency, especially in transactional systems. This can lead to data anomalies and a higher risk of data corruption if not managed carefully. Professional reasoning. Professionals should approach such migration challenges by first thoroughly understanding the existing application's data model, its usage patterns, and the business requirements. This understanding forms the basis for evaluating potential data model adjustments. A phased approach, involving analysis, design, implementation, and rigorous testing, is crucial. The decision-making process should prioritize solutions that optimize for the target cloud environment, Azure SQL database, while ensuring data integrity, performance, and cost-effectiveness. Professionals must weigh the trade-offs between different modeling techniques, normalization vs. denormalization, indexing strategies, etc., based on empirical evidence gathered during testing and performance monitoring. Question 11. Regulatory review indicates a need to create new Azure SQL databases with strict adherence to organizational security policies and data governance standards. Which of the following approaches best ensures compliance and operational efficiency for provisioning these databases? Option A. Manually configure each Azure SQL database through the Azure portal, focusing on essential settings and addressing security configurations as a separate post-deployment task. Option B. Delegate the creation of Azure SQL databases to development teams, providing them with broad permissions and relying on their individual security practices. Option C. Utilize Azure PowerShell scripts or Azure CLI commands to define and deploy the Azure SQL databases, incorporating security configurations, network rules, and access policies directly into the scripts. Option D. Provision Azure SQL databases using the Azure portal with default security settings, and schedule a future review to implement necessary compliance measures. The correct answer is C. Utilize Azure PowerShell scripts or Azure CLI commands to define and deploy the Azure SQL databases, incorporating security configurations, network rules, and access policies directly into the scripts. Explanation. This scenario presents a common challenge for Azure database administrators, ensuring compliance with organizational policies and regulatory requirements when provisioning new Azure SQL databases. The challenge lies in balancing the need for rapid deployment with the imperative to adhere to security and governance standards. A robust decision-making process is crucial to avoid security vulnerabilities, data breaches, and non-compliance penalties. The correct approach represents best professional practice because it leverages automated, script-based deployment methods that are inherently repeatable, auditable, and configurable to enforce specific security settings and compliance policies from the outset. Using Azure PowerShell or Azure CLI allows for the definition of infrastructure as code, which can be version controlled and integrated into CI/CD pipelines. This ensures that every database deployed adheres to the defined security posture, including network access controls, encryption settings, and identity management, thereby meeting regulatory obligations for data protection and access control. An incorrect approach that involves manual configuration through the Azure portal without a documented, repeatable process poses significant regulatory and ethical risks. Manual steps are prone to human error, leading to misconfigurations that could expose sensitive data or violate access control policies. This lack of standardization makes auditing difficult and increases the likelihood of noncompliance with data privacy regulations. Furthermore, relying solely on manual configuration bypasses opportunities for automated security checks and policy enforcement, which are critical for maintaining a secure and compliant environment. Another incorrect approach, deploying with default security settings and planning to remediate later, is highly problematic. This introduces a window of vulnerability where the database is not adequately protected, potentially violating data protection laws and organizational security policies. The ethical failure here is the acceptance of unnecessary risk to sensitive data. Professional decision-making in such situations should involve a risk-based assessment, prioritizing secure-by-design principles. When provisioning resources, administrators must proactively implement security controls that align with regulatory requirements, rather than treating security as an afterthought. This involves understanding the specific compliance mandates, e.g., GDPR, HIPAA, if applicable to the exam's assumed jurisdiction, and ensuring that the chosen deployment method and configuration directly address those mandates. Question 12. The control framework reveals that the Azure database for PostgreSQL instance supporting a critical customer-facing application in the East U.S. region has experienced intermittent connectivity issues due to localized network disruptions. To mitigate future risks of prolonged downtime and data loss during a regional outage, the IT operations team is evaluating strategies to enhance disaster recovery capabilities. We need to ensure that in the event of a complete failure of the East U.S. Azure region, the application can resume operations with minimal data loss and within acceptable recovery time objectives. Which of the following approaches best addresses the disaster recovery requirements for this Azure database for PostgreSQL instance? Option A. Manually export the database schema and data to flat files on a weekly basis and store them on a local workstation. Option B. Implement a high availability solution within the East U.S. region, such as zone redundancy, to protect against single data center failures. Option C. Configure georeplication to create a read-only replica of the database in a geographically distant Azure region, and establish a documented process for promoting this replica to a primary instance during a disaster. Option D. Increase the frequency of automated backups for the database and store them in a separate Azure storage account within the same East U.S. region. The correct answer is C. Configure georeplication to create a read-only replica of the database in a geographically distant Azure region, and establish a documented process for promoting this replica to a primary instance during a disaster. Explanation. This scenario presents a common challenge in cloud database administration, ensuring business continuity and data availability in the face of potential regional outages. The professional challenge lies in balancing cost, performance, and compliance requirements while implementing a robust disaster recovery strategy. Azure Database for PostgreSQL's georeplication capabilities are central to this, but understanding their implications for RPO, recovery point objective, and RTO, recovery time objective, is critical. Regulatory compliance, while not explicitly stated as a specific jurisdiction in the prompt, implies adherence to general data protection principles and industry best practices for availability and resilience, which are universally applicable in professional IT environments. The correct approach involves leveraging Azure's built-in georeplication to create a read-only replica in a different Azure region. This is best professional practice because it directly addresses the RPO and RTO requirements by providing a near real-time copy of the data that can be promoted to a primary in the event of a disaster. This minimizes data loss and allows for a swift recovery, aligning with typical business expectations for availability. The inherent redundancy provided by georeplication is a fundamental component of a sound disaster recovery plan, ensuring that critical data remains accessible even if the primary region becomes unavailable. An incorrect approach would be to rely solely on automated backups without considering their restore time and the potential for data loss. While backups are essential for data protection, they are not a substitute for active georeplication when the goal is to minimize downtime and data loss during a regional outage. Regulatory or ethical failure here is a lack of due diligence in understanding the limitations of a backup-only strategy for disaster recovery, potentially leading to unacceptable data loss and extended downtime, which could violate service-level agreements or data protection mandates. Another incorrect approach would be to implement georeplication, but fail to regularly test the failover process. The professional failure is in assuming that a configured solution will work without validation. This oversight can lead to a catastrophic failure during a real disaster, as the failover mechanism may not function as expected, rendering the disaster recovery plan ineffective. This demonstrates a lack of rigorous testing and validation, which is a cornerstone of professional IT operations. A third incorrect approach would be to choose a secondary region that is geographically too close to the primary region. While this might reduce latency for read-only replicas, it fails to provide true disaster recovery against a widespread regional event. The professional and ethical failure is in misunderstanding the fundamental purpose of georeplication for disaster recovery, which is to protect against large-scale failures affecting an entire geographic area. This approach would not meet the resilience requirements of a robust disaster recovery plan. The professional decision-making process for similar situations should involve a thorough assessment of RPO and RTO requirements, understanding the capabilities and limitations of available technologies, like Azure's geo-replication, and implementing a comprehensive testing and validation strategy. It also requires considering the geographic diversity needed to mitigate risks associated with regional failures. Question 13. Cost-benefit analysis shows that migrating an on-premises SQL Server database to Azure SQL database could offer significant cost savings. However, the organization has strict uptime requirements and a need to maintain data integrity and security throughout the migration process. Which of the following migration approaches best balances these competing priorities while adhering to Azure's regulatory framework and best practices for database administration? Option A. Utilize Azure Database Migration Service, DMS, for a phased migration, including pre-migration assessments, pilot testing, and a well-defined rollback strategy, while ensuring all Azure security and compliance features are configured. Option B. Prioritize the fastest possible migration by disabling all security features and compliance checks during the transfer to reduce overhead. Option C. Migrate the database to a self-managed virtual machine in Azure and then manually configure all database settings and security. Option D. Perform a direct, in-place migration of the entire database during a single maintenance window without extensive pre-migration testing or a rollback plan. The correct answer is D. Perform a direct, in-place migration of the entire database during a single maintenance window without extensive pre-migration testing or a rollback plan. Explanation. Scenario analysis. This scenario presents a common challenge in Azure Database Administration, migrating a critical on-premises SQL Server database to Azure SQL Database. The professional challenge lies in balancing the immediate cost savings identified in the initial analysis with the long-term operational efficiency, security, and compliance requirements mandated by Azure's regulatory framework and best practices. A hasty decision based solely on upfront cost can lead to significant technical debt, security vulnerabilities, and compliance issues, ultimately costing more in the long run. Careful consideration of the migration strategy's impact on data integrity, availability, performance, and security is paramount. Correct approach analysis. The correct approach involves a phased migration strategy that prioritizes minimizing downtime and ensuring data consistency. This typically includes thorough pre-migration assessment, pilot testing with a subset of data or non-production workloads, and a well-defined rollback plan. Utilizing Azure Database Migration Service, DMS, or similar Azure-native tools is crucial as they are designed to handle complex migrations with minimal disruption and adhere to Azure's security and compliance standards. This approach ensures that the migration process is robust, auditable, and minimizes the risk of data loss or extended downtime, which are critical for maintaining business continuity and meeting regulatory obligations for data availability and integrity. Incorrect approaches analysis. An approach that involves a direct, lift-and-shift migration without adequate pre-migration assessment or testing is professionally unacceptable. This method often overlooks compatibility issues, performance bottlenecks, and security misconfigurations that can arise when moving from an on-premises environment to a managed cloud service. Such a failure to assess and plan can lead to data corruption, extended unplanned downtime, and security vulnerabilities that violate Azure's security principles and potentially regulatory requirements for data protection. Another incorrect approach would be to migrate without a comprehensive rollback strategy. This creates a significant risk of irreversible data loss or system failure if the migration encounters unforeseen issues. The absence of a rollback plan demonstrates a lack of due diligence and a disregard for business continuity, which is a fundamental ethical and professional responsibility. It also fails to meet potential regulatory requirements for disaster recovery and business continuity planning. Finally, choosing a migration method that bypasses Azure's native security features or compliance controls, such as manually configuring network security groups or not leveraging Azure's built-in encryption, is also professionally unsound. This can expose sensitive data to unauthorized access and violate Azure's security posture and compliance certifications, leading to potential data breaches and regulatory penalties. Professional reasoning. Professionals should approach database migration by first conducting a comprehensive assessment of the existing environment, including application dependencies, data volume, performance requirements, and security needs. This assessment should inform the selection of the most appropriate migration strategy, considering tools like Azure DMS. A phased approach with rigorous testing, a clear rollback plan, and a focus on leveraging Azure's native security and compliance features is essential. This systematic process ensures that the migration is not only cost-effective in the short term, but also sustainable, secure, and compliant in the long term, aligning with professional ethics and regulatory expectations for responsible cloud adoption. Question 14. Market research demonstrates that a critical customer-facing application hosted on Azure Cosmos DB is experiencing intermittent performance degradation during peak usage hours. As the Azure Database Administrator Associate, which approach best addresses this challenge while considering cost-effectiveness and service continuity? Option A. Immediately increase the provision request units per second (RU/S) across the board to ensure the application can handle any load. Option B. Reduce the provisioned RU/S to a baseline level to minimize costs, assuming the performance issues are temporary. Option C. Rely on the default RU settings for the database, as Azure automatically optimizes performance. Option D. Analyze the application's actual request unit consumption patterns during various load conditions and adjust the provision throughput accordingly. The correct answer is D. Analyze the application's actual request unit consumption patterns during various load conditions and adjust the provision throughput accordingly. Explanation. Scenario analysis. This scenario presents a common challenge for Azure Database Administrators: optimizing performance and cost for a critical application without compromising service availability or data integrity. The risk lies in misinterpreting request units, RU, and their impact, potentially leading to either over-provisioning, unnecessary cost, or under-provisioning, performance degradation, and user dissatisfaction. The professional challenge is to balance these competing demands based on a nuanced understanding of RU behavior within the Azure Cosmos DB ecosystem, adhering to best practices for resource management and cost optimization. Correct approach analysis. The correct approach involves understanding that RUs represent a normalized measure of database throughput. By analyzing the application's actual consumption patterns, particularly during peak and off-peak hours, and correlating this with the defined RU/S, request units per second, for the database, an administrator can make informed decisions. This approach aligns with professional best practices by focusing on data-driven insights to right-size resources. It ensures that the provision throughput meets the application's demands without excessive waste, thereby optimizing cost-effectiveness while maintaining performance. This proactive monitoring and adjustment directly supports the principle of efficient resource utilization, a key tenet of cloud administration. Incorrect approaches analysis. One incorrect approach is to solely rely on default RU settings provided by Azure. This fails to account for the specific workload characteristics of the application, leading to either over-provisioning and wasted expenditure, or under-provisioning and performance issues. Ethically, this can be seen as a failure to exercise due diligence in managing client or organizational resources effectively. Another incorrect approach is to arbitrarily increase RUs based on anecdotal user complaints without a thorough investigation of the underlying cause. This can lead to unnecessary cost increases and does not address the root problem, potentially masking other performance bottlenecks. Professionally, this demonstrates a lack of systematic problem solving and a reactive rather than proactive stance. A third incorrect approach is to focus solely on cost reduction by drastically lowering RUs without considering the potential impact on application performance and availability. This can lead to service disruptions, data latency, and a negative user experience, which is professionally unacceptable and can have significant business implications. Professional reasoning. Professionals should adopt a data-driven iterative approach. This involves 1. Monitoring current RU consumption using Azure Monitor and Cosmos DB metrics. 2. Identifying peak and average usage patterns. 3. Correlating RU consumption with specific application operations. 4. Using this analysis to determine the appropriate RU/S for the workload. 5. Implementing auto-scaling or manual adjustments based on observed trends. 6. Regularly reviewing and re-evaluating RU settings as application usage evolves. This systematic process ensures that resources are optimally allocated, costs are managed, and performance is maintained, reflecting a commitment to professional responsibility and efficient cloud resource management. Question 15. Market research demonstrates that a company is increasingly storing sensitive customer financial data with an Azure SQL database. The company operates under a general framework of data protection regulations that mandate the safeguarding of personal financial information. As the Azure database administrator, you need to implement a robust encryption strategy to protect this data both at rest and in transit, while also considering the security of highly sensitive individual data fields. Which approach best balances security, compliance, and manageability for this scenario? Option A. Encrypt only data in transit using SSL/TLS connections, as this is the primary concern for financial data security. Option B. Develop and implement a custom, application-level encryption solution for all financial data before it is written to the database, and rely on SSL/TLS for transit. Option C. Implement transparent data encryption, TDE, for the entire Azure SQL database to protect data at rest, and configure always encrypted for specific columns containing highly sensitive financial details like credit card numbers. Ensure SSL/TLS is enabled for connections to encrypt data in transit. Option D. Enable transparent data encryption, TDE, for the database and ensure all application connections use SSL/TLS, but do not implement granular encryption for specific sensitive fields. The correct answer is C. Implement transparent data encryption, TDE, for the entire Azure SQL database to protect data at rest, and configure always encrypted for specific columns containing highly sensitive financial details like credit card numbers. Ensure SSL/TLS is enabled for connections to encrypt data in transit. Explanation. This scenario is professionally challenging because it requires balancing robust data security with operational efficiency and compliance. The administrator must understand the nuances of different encryption methods to select the most appropriate solution for sensitive customer data stored in Azure SQL database, considering potential impacts on performance and manageability. Careful judgment is required to ensure that the chosen encryption strategy not only protects data at rest and in transit, but also adheres to relevant data protection regulations without introducing undue complexity or cost. The correct approach represents best professional practice because it directly addresses the core requirement of protecting sensitive data using Azure's built-in encryption capabilities, specifically transparent data encryption, TDE, for data at rest, and always encrypted for sensitive columns. TDE provides comprehensive protection for the entire database, encrypting the data files and transaction logs. Always encrypted offers granular protection for highly sensitive data within the database, such as credit card numbers or personally identifiable information, PI, by encrypting it at the client driver level. This layered approach ensures data is protected both when stored and when accessed by authorized applications, aligning with the principle of defense in depth. From a regulatory perspective, implementing these encryption methods helps meet compliance obligations for data protection and privacy, such as those that might be stipulated by general data protection principles applicable within the scope of Azure services. An incorrect approach that relies solely on application-level encryption without leveraging TDE or always encrypted is professionally unacceptable. This would likely result in inconsistent protection, as not all data might be encrypted, and it would place a significant burden on application developers to manage encryption keys and logic, increasing the risk of errors and vulnerabilities. Furthermore, it fails to address data at rest comprehensively, leaving sensitive data exposed if the database files themselves are compromised. This approach could lead to regulatory noncompliance if specific data protection mandates require encryption of data at rest or in transit. Another incorrect approach that involves encrypting only data in transit using SSL/TLS but neglecting data at rest encryption is also professionally deficient. While encrypting data in transit is crucial, it does not protect data once it has been written to disk. If the database files are accessed directly or if a backup is compromised, the data would be exposed. This oversight would violate the principle of protecting data throughout its lifecycle and could lead to significant data breaches, resulting in severe regulatory penalties and reputational damage. A third incorrect approach that focuses on encrypting all data using a single, custom-built encryption solution without considering Azure's native capabilities is professionally unsound. Custom encryption solutions are often complex to implement, maintain, and audit. They can introduce performance bottlenecks and are more prone to security vulnerabilities if not expertly designed and managed. Relying on native, well-vetted Azure services like TDE and always encrypted is generally more secure, cost-effective, and easier to manage, ensuring better compliance and operational stability. The professional decision-making process for similar situations should involve a thorough risk assessment. This includes identifying sensitive data, understanding regulatory requirements, evaluating the capabilities and limitations of available security technologies, both native cloud services and third-party solutions, and considering the impact on application performance and manageability. The administrator should prioritize solutions that offer comprehensive protection, are compliant with relevant regulations, and are manageable within the operational environment. A layered security approach, leveraging the strengths of different encryption methods, is typically the most robust and professionally responsible strategy. Question 16. Benchmark analysis indicates that an organization is migrating a critical application that accesses sensitive customer data stored in Azure SQL database. The application resides within an Azure virtual network. To ensure the highest level of security and compliance, what is the most effective network security approach for connecting the application to the Azure SQL database? Option A. Configure the Azure SQL database firewall to allow access from all IP addresses. Option B. Configure the Azure SQL database firewall to allow access from the organization's public IP addresses. Option C. Implement a service endpoint for Azure SQL database on the virtual network. Option D. Implement Azure Private Link with a private endpoint in the virtual network to establish a private connection to the Azure SQL database. The correct answer is B. Configure the Azure SQL database firewall to allow access from the organization's public IP addresses. Explanation: Scenario analysis. This scenario presents a common challenge for Azure database administrators, balancing robust network security with the operational needs of applications accessing sensitive data. The core difficulty lies in implementing security measures that effectively prevent unauthorized access and data exfiltration, while ensuring legitimate users and services can perform their functions without undue disruption. Misconfigurations can lead to security breaches, compliance violations, or application downtime, all of which have significant business implications. The need for granular control over network traffic to a critical database resource necessitates a deep understanding of Azure networking constructs and security best practices. Correct approach analysis. The correct approach, utilizing Azure Private Link with a private endpoint, represents best professional practice because it establishes a private, secure connection from the virtual network to the Azure SQL database. This bypasses the public internet entirely, significantly reducing the attack surface. Azure Private Link adheres to the principle of least privilege by allowing network traffic to flow directly from the virtual network to the database service without exposing it to public endpoints. This aligns with regulatory frameworks that mandate data protection and secure data transmission, as it minimizes the exposure of sensitive data to potential threats. It also provides enhanced control and auditability of network access. Incorrect approaches analysis. Allowing access from all IP addresses, even with a firewall rule, is a significant regulatory and ethical failure. This approach violates the principle of least privilege and creates an unnecessarily large attack surface. It is highly probable that such an open configuration would contravene data protection regulations, e.g., GDPR, HIPAA, depending on the specific data context. Though for this exam, we focus on general Azure best practices that align with common regulatory principles, by failing to implement adequate safeguards against unauthorized access. Ethically, it demonstrates a lack of due diligence in protecting sensitive data. Configuring the Azure SQL database firewall to allow access only from the organization's public IP addresses, while better than allowing all IPs, is still not the most secure or best practice approach for internal application access. This method relies on the security of the organization's perimeter network and can be vulnerable if that perimeter is compromised. Furthermore, it does not provide the granular control offered by Private Link and still exposes the database to the public internet, albeit with a restricted source. This can be seen as a failure to implement the most effective security controls available, potentially leading to non-compliance with data security mandates that require minimizing exposure. Implementing a service endpoint for the Azure SQL database from the virtual network is a step towards better security than public access, as it restricts access to traffic originating from the virtual network. However, it still relies on the public endpoint of the Azure SQL database, and traffic is routed over the Azure Backbone network, not a private connection. While it enhances security by restricting access to the VNet, it does not offer the same level of isolation and security as Private Link, which completely removes the database from the public internet. This approach might be considered a partial failure to implement the most robust security posture available, potentially falling short of stringent data protection requirements. Professional reasoning. Professionals should approach network security by first understanding the data sensitivity and compliance requirements. The principle of least privilege should guide all security decisions. When connecting applications to Azure PaaS services like Azure SQL Database, the primary consideration should be to avoid public internet exposure whenever possible. Evaluating available Azure networking security features, such as private link, service endpoints, and firewall rules, is crucial. The decision should prioritize solutions that offer the most granular control, the smallest attack surface, and the highest degree of isolation. In this context, Private Link with private endpoints offers the most secure and compliant solution for private connectivity. Question 17. Risk assessment procedures indicate that a global e-commerce application hosted on Azure SQL Database is experiencing performance degradation due to high latency for users in Asia and Europe, while the primary database instance is located in North America. The application requires a high degree of data availability and must adhere to data residency principles for customer data. The current configuration uses a single primary replica with session consistency. The administration team needs to optimize the deployment to improve user experience and maintain data integrity. Option A. Migrate the primary database instance to an Azure region in Asia to reduce latency for the largest user segment and maintain session consistency across all replicas. Option B. Deploy read replicas in every available Azure region to maximize global availability and enforce strong consistency for all database operations. Option C. Deploy read replicas in Azure regions geographically closer to the Asian and European user bases, and configure the primary replica with session consistency for most operations, while evaluating the need for stronger consistency for specific critical transactions. Option D. Keep the primary database instance in North America and implement geo-failover to a secondary replica in Europe, maintaining session consistency for all read operations. The correct answer is C. Deploy read replicas in Azure regions geographically closer to the Asian and European user bases and configure the primary replica with session consistency for most operations, while evaluating the need for stronger consistency for specific critical transactions. Explanation. Scenario analysis. This scenario presents a common challenge for Azure database administrators: balancing performance, availability, and cost while adhering to regulatory compliance for data residency and access. The need to support a global user base with varying latency requirements and the mandate for specific data consistency levels introduce complexity. The challenge lies in selecting the optimal Azure region and replication strategy without compromising data integrity or incurring unnecessary expenses, all within the confines of the exam's specified regulatory framework, which, for this exam, implies adherence to Microsoft's Azure Service Agreements and general data protection principles as they apply to cloud services. Correct approach analysis. Choosing an Azure region that is geographically closest to the majority of the user base and also meets the data residency requirements is paramount. For read-heavy workloads and to minimize latency for geographically dispersed users, implementing read replicas in regions closer to those users is a best practice. This approach directly addresses the performance and availability requirements. Furthermore, selecting a consistency level that balances data freshness with performance, e.g., session consistency for most operations, with stronger consistency for critical transactions if absolutely necessary, is crucial. This demonstrates an understanding of the trade-offs inherent in distributed database systems and aligns with efficient resource utilization. This approach represents best professional practice by prioritizing user experience, operational efficiency, and compliance with data residency principles inherent in cloud service usage. Incorrect approach is analysis. Deploying the primary database in a region far from the majority of users, solely to minimize the cost of a single instance, would lead to unacceptable latency for a significant portion of the user base, negatively impacting application performance and user satisfaction. This fails to meet the implied professional obligation to provide a performance service. Implementing read replicas in every available Azure region without considering user proximity or workload demand is an inefficient use of resources, leading to unnecessary costs and increased management overhead. This demonstrates a lack of strategic planning and cost consciousness. Selecting the strongest consistency level, e.g., strong consistency, for all operation, even read-heavy ones, can significantly impact performance and increase latency, negating the benefits of read replicas and potentially hindering application responsiveness. This shows a misunderstanding of consistency models and their performance implications. Professional reasoning. Professionals should approach this by first identifying the primary user locations and any data residency mandates. Then, they should evaluate Azure regions based on proximity, available services, and cost. For read-heavy workloads, consider read replicas strategically placed to serve user groups in different geographical areas. Finally, carefully select the consistency level that best balances data freshness requirements with application performance needs, understanding the trade-offs involved. This iterative process of assessment, planning, and optimization ensures that technical solutions align with business objectives and user expectations. Question 18. Investigation of a critical Azure SQL database instance reveals that the current automated backup retention policy is set to the default 7-day period. The business has recently implemented new data governance policies requiring a minimum of 30 days of point-in-time restore capability for all production databases. The database administrator needs to ensure compliance and data recoverability without introducing significant manual overhead or compromising performance. What is the most appropriate action to take? Option A. Implement a custom script to export transaction logs to Azure Blob Storage daily and restore from these logs. Option B. Configure the automated backup retention period for the Azure SQL database to 30 days. Option C. Manually schedule full backups to Azure Blob Storage every 24 hours and retain them for 30 days. Option D. Disable automated backups and rely on manual snapshots taken weekly. Correct answer is B. Configure the automated backup retention period for the Azure SQL database to 30 days. Explanation. Scenario analysis. This scenario presents a common challenge in cloud database administration, ensuring data recoverability while optimizing resource utilization and adhering to compliance requirements. The challenge lies in balancing the need for robust backup and restore capabilities against the potential costs and complexities of managing them. A critical aspect is understanding the default behaviors of Azure SQL database backup policies and how to effectively customize them to meet specific recovery point objective (RPO) and recovery time objective (RTO) needs, all within the context of Azure's service level agreements and potential regulatory mandates for data retention and availability. Correct approach analysis. The correct approach involves leveraging Azure SQL database's automated backup features, specifically by configuring retention policies that align with business and regulatory requirements. Azure SQL database automatically performs full, differential, and transaction log backups, which are retained for a configurable period. By default, this retention is 7 days for general purpose and business critical tiers, and 7 days for basic and standard tiers. However, this can be extended up to 35 days. For longer retention, geo-replicated backups or Azure Blob Storage can be utilized. This approach represents best professional practice because it directly addresses the core requirement of data recoverability through a managed, built-in service. It ensures that point-in-time restore, PITR, capabilities are available within the defined retention period, meeting RPO and RTO targets without requiring manual intervention for routine backups. This aligns with the principle of least privilege and efficient resource management, as Azure handles the backup infrastructure. Furthermore, by explicitly configuring retention, the administrator ensures compliance with any data retention policies mandated by industry regulations or internal governance, preventing accidental data loss due to insufficient retention or unnecessary storage costs from overretention. Incorrect approach is analysis. One incorrect approach is relying solely on the default 7-day retention period without verification. This is professionally unacceptable because it fails to proactively assess and meet specific business or regulatory requirements for data retention. If a longer retention period is needed, this default setting would lead to data loss beyond the 7-day window, violating potential compliance mandates and business continuity plans. Another incorrect approach is manually creating full backups to Azure Blob Storage on a fixed schedule without leveraging Azure SQL Database's automated capabilities. While this provides a backup, it introduces significant operational overhead, increases the risk of human error in scheduling and management, and bypasses the integrated, highly available backup infrastructure provided by Azure. This can lead to inconsistencies in backup coverage and a slower restore process compared to automated PITR. A third incorrect approach is disabling automated backups entirely to save costs. This is a severe regulatory and ethical failure, as it completely removes the ability to recover data in case of accidental deletion, corruption, or disaster, directly contravening the fundamental responsibility of data protection and business continuity. It would likely violate numerous data protection regulations and service-level agreements. Professional reasoning. Professionals should approach this scenario by first understanding the specific RPO and RTO requirements for the Azure SQL database. This involves consulting with stakeholders, reviewing business continuity plans, and identifying any relevant regulatory or compliance mandates regarding data retention and availability. The next step is to evaluate Azure SQL database's built-in automated backup features and their configuration options, particularly the retention period. If the default retention meets the requirements, it should be confirmed. If not, the retention period should be adjusted accordingly. For longer retention needs, professionals should investigate options like geo-replicated backups or exporting data to Azure Blob Storage. The decision-making process should prioritize leveraging managed services for reliability and efficiency, while ensuring that all configurations align with defined recovery objectives and compliance obligations. Regular review and testing of restore procedures are also critical components of professional practice. Question 19. What factors determine the most appropriate vCore-based purchasing model for an Azure SQL database deployment from a stakeholder perspective? Option A. A generic recommendation based on common industry practices for similar applications, without detailed workload analysis. Option B. The specific workload characteristics, including CPU, memory, storage, and IOPS requirements, coupled with the business objectives for performance, availability, and budget constraints. Option C. The model that offers the lowest initial purchase price, regardless of its suitability for the intended workload. Option D. The purchasing model with the highest available performance specifications to ensure future-proofing and avoid potential performance bottlenecks. Correct answer is B. The specific workload characteristics, including CPU, memory, storage, and IOPS requirements, coupled with the business objectives for performance, availability, and budget constraints. Explanation. Scenario analysis. This scenario is professionally challenging because selecting the appropriate vCore-based purchasing model for Azure SQL database involves balancing cost optimization with performance and scalability needs, all within the context of Azure Service Level Agreements, SLAs, and licensing terms. A miscalculation can lead to unexpected expenses or under-provisioned resources, impacting business operations and stakeholder satisfaction. The decision requires a thorough understanding of the client's current and projected workload, their tolerance for upfront investment versus ongoing operational expenditure, and the specific benefits offered by each purchasing model. Correct approach analysis. The correct approach involves a comprehensive assessment of the client's workload characteristics, including IOPS, CPU, memory, and storage requirements, alongside their business objectives for performance, availability, and budget. This aligns with best practices for cloud resource management, emphasizing a data-driven and needs-based selection. Azure's vCore model is designed to offer flexibility, allowing organizations to choose between the general purpose, business-critical, and hyperscale tiers, each with different performance characteristics and pricing structures. Understanding the nuances of these tiers and how they map to specific workload demands is crucial for making an informed decision that maximizes value and minimizes waste. This approach directly addresses the core purpose of the vCore model, providing granular control over compute and storage resources to match application needs, thereby ensuring cost-effectiveness and performance. Incorrect approaches analysis. Choosing a model solely based on the lowest upfront cost without considering performance implications is a regulatory and ethical failure. This can lead to underprovisioning, violating the implicit agreement to provide a functional and performance service, and potentially breaching SLAs if performance targets are not met. It also represents poor financial stewardship. Conversely, selecting the highest performance tier without a clear business justification is a failure in cost management and resource optimization. This leads to unnecessary expenditure, which can be seen as a breach of fiduciary duty to the client or organization, as it wastes resources that could be allocated elsewhere. Relying on generic recommendations or defaulting to a single tier without analyzing specific workload needs ignores the fundamental principle of tailoring cloud solutions to individual requirements, leading to suboptimal outcomes and potential compliance issues related to resource utilization and cost accountability. Professional reasoning. Professionals should adopt a structured decision-making process that begins with a deep dive into the client's application workload and business requirements. This involves gathering metrics on current resource utilization, understanding future growth projections, and defining acceptable performance and availability thresholds. Subsequently, they should map these requirements to the capabilities and pricing of Azure SQL databases, vCore purchasing models, general purpose, business critical, hyperscale. A cost-benefit analysis should then be performed for each viable option, considering not just the direct costs, but also the potential impact on application performance and user experience. Regular review and optimization of the chosen model are also essential to ensure continued alignment with evolving needs and to capitalize on any new Azure offerings or pricing changes.